Welcome back to the workshop. Module 6 is on asphalt or flexible pavement and semi-rigid pavement design strategies using the Pavement ME software. We just finished explaining the rut depth models and transfer functions. This session, or Module 6-1-2, will focus on the models and transfer functions used to predict transverse cracks in asphalt wearing surfaces. There are 5 learning outcomes of Module 6-1-2, which include: define and explain transverse cracking of the asphalt wearing surface layer of flexible pavements. Describe the mechanism that caused transverse cracks in flexible pavements. Describe the fracture mechanics approach or concept used to predict transverse cracks. Describe the models and transfer functions used to predict transverse cracks. And finally, list the asphalt wearing surface property and test procedures needed in support of the transverse cracking transfer function. This session is grouped into 3 parts as discussed for the other flexible pavement and rigid pavement distresses. The first is to define and measure transverse cracks, or the definition and measurement of transverse cracks. The second is the transverse cracking mechanism. And the third is a transfer function used to predict transverse cracks. As part of the third group, the asphalt wearing surface layer properties and test procedures needed in support of the models and transfer function will be discussed and listed. So let's start with the definition and measurement of transverse cracks. Transverse cracks are fractures that are predominantly perpendicular to the roadway centerline. Transverse cracks can be full width across the lane or partially extend across the lane. Both full lane width and partial lane width transverse cracks were counted and measured in linear feet as part of the calibration process. Transverse cracks are non-wheel load related cracks that are a result of the combination of climate and the properties of the wearing surface. In other words, they are independent of wheel loads and truck traffic, but heavily dependent on climate and material properties. There are 2 types of non-wheel load-related transverse cracks, which are defined as transverse cracks and block cracks. Block cracking is a continuation of transverse cracks, but at a closer spacing combined with longitudinal cracks, as illustrated in the photograph on the right of the slide. Transverse cracks are measured in linear feet or distance, while block cracks are measured on an area basis in terms of the long-term pavement performance program. The Pavement ME design software does not predict block crack. It only predicts transverse cracking. Transverse cracks within block cracks, however, should be counted and used or measured and used in terms of transverse cracking. Now let's discuss the mechanism simulated in the Pavement ME software for predicting transverse cracks. As noted earlier within this module, transverse cracks are non-wheel load related cracks. They occur from low temperatures or cold temperature events over time when the tensile stress from a drop in temperature exceeds the tensile strength of the asphalt mixture. Binder aging of the asphalt wearing surface is another cause or mechanism of transverse cracks. So, binder aging superimposed with critical low temperature events is used to predict cracking. Temperature cycles or variations can also result in transverse cracks through thermal fatigue, which is the continued application of tensile stresses at the surface of the asphalt, or the repeated application of tensile stresses at the surface of the asphalt. Another mechanism for transverse cracks is the shrinkage of the asphalt mixture or wearing surface. However, shrinkage of the asphalt layers is not included as a mechanism or used to predict transverse cracks in the Pavement ME design software. This slide graphically illustrates the increase in tensile strength and tensile stress as the temperature decreases. A crack occurs when the tensile stress exceeds the strength. Microcracks begin to occur between the asphalt binder and aggregate at very low temperatures that affect the adhesion and strength of the mixture. The temperature at which this occurs is mix and binder dependent. The maximum tensile strength of the asphalt wearing surface in the Pavement ME design software is defined at 14 degrees Fahrenheit, which remains constant at colder temperatures. This is a simplification of the mechanism included in the Pavement ME design software. In other words, the thermal stress as the temperature decreases will continually build up at the surface of the wearing surface. Continuous decrease in temperature results in a continuous increase in tensile stress. The indirect tensile strength of the mix will also increase with decreases in temperature. But then, as the temperatures continue to get colder, there is a decrease in the indirect tensile strength simulated that is caused by the microcracks between the asphalt binder interface and aggregate. That condition is not simulated in the Pavement ME design software. So the Pavement ME design software assumes a maximum cracking strength or an indirect tensile strength at 14 degrees Fahrenheit, which remains constant or assumed to remain constant as the temperature continues to decrease with climate or throughout the day and or month. If transverse cracks were predominantly caused by low temperatures, transverse cracking would not occur in warm or hot temperatures. However, transverse cracking is a common distress in warm climates. Thus, the mechanism is more than just a combination of low and cold temperature events. Shrinkage and thermal fatigue play an important role in the occurrence of transverse cracks. So transverse cracks can occur in both cold as well as warm and or hot climates. Now let's explain and discuss the transfer function used to predict transverse cracks with the condition that they can occur in both cold to hot climates. Remember from Module 2, the critical pavement responses are used to determine or calculate damage in the case of transverse cracks, and the transfer function converts the thermal damage to what we can see and measure on the pavement surface, the length of transverse cracks. The primary response is a tensile stress at the surface of the asphalt wearing surface from low temperature events. In addition, the tensile stress intensity factors are also used as a damage value to predict the length of transverse cracks. The flow chart or diagram displayed in this slide provides an overall flow of the information and models needed for predicting the length of transverse cracks. The basic inputs are for the enhanced integrated climatic model and pavement response programs to calculate the tensile stress and stress intensity factors at the crack tip, which is the critical responses for predicting transverse cracks. The indirect tensile test measured in accordance or performed in accordance with AASHTO T322 provides the key layer properties needed for predicting transverse cracks. The fracture mechanics approach is used in relating the tensile stress at the crack tip and change in the stress intensity factors to the length of transverse cracks depending on the thickness of the asphalt layer. So the inputs to the model include both climate and responses. Climate being from the enhanced integrated climatic model, the pavement response model, or simply the tensile stress and stress intensity factors at the crack tip. The indirect tensile test provides the strength and creep compliance of the asphalt mixture. The responses are then used as well as the mixture properties are then used in fracture mechanics to look at how transverse cracks will propagate in and through the asphalt layer with the use of fracture mechanics to determine the length of transverse cracking as predicted by the Pavement ME design software. This slide illustrates in a simplified form the flow for predicting the length of transverse cracks. The indirect tensile creep compliance test and the coefficient of thermal expansion and contraction are used to calculate the thermal stress using the temperatures from the enhanced integrated climatic model. The indirect tensile strength and creep compliance test are used with the fracture mechanics approach to calculate crack initiation and the length of transverse cracks over time. The thermal stress and the tensile stress intensity factors at the crack tips after crack initiation is estimated using the coefficient of thermal expansion and contraction, and the creep compliance of the asphalt wearing surface. The software assumes the asphalt layer or mixture is uniform with depth for each layer. More importantly, the properties from the asphalt wearing surface are only used to calculate the length of transverse cracks. The properties of any other asphalt layer, if included in the Pavement ME design software run, are not used for predicting transverse cracks. Examples of the creep compliance test results are displayed on this slide. In other words, two examples are provided, as shown on the graphs on the left hand of the slide. One is for an asphalt mixture that has high wrap content, and the other is for a polymer modified asphalt without wrap. Both show creep compliance in terms of the creep compliance as a function of loading time, as a function of three different temperatures that are used in the program. 0 degrees centigrade, a minus 10 degrees centigrade, and a minus 30 degrees centigrade. The reference temperature used to determine the creep compliance master curve is a minus 20 degrees centigrade. The more compliant the asphalt mixture or layer is, the thermal stresses build up at a slower rate because of the relaxation of the tensile stresses calculated by the program. So the more compliant the mix, the lower the tensile stresses, or the greater the relaxation of the tensile stresses at the surface of the asphalt pavement. And again, creep compliance is measured in accordance with AASHTO T322. The coefficient of thermal expansion and contraction is calculated by the software because there is no ASTM or AASHTO test standard for measuring the coefficient of thermal expansion or contraction. The calculated thermal expansion contraction was used for the global calibration process. The coefficient of thermal expansion contraction is calculated from the volumetric properties of the wearing surface, which will be illustrated on the next slide. However, some agencies have reduced the area of the transverse cracking transfer function by deriving the coefficient of thermal expansion contraction through local calibration for specific aggregates and or asphalt mixture types. The equation used to calculate the coefficient of thermal expansion contraction is displayed on this slide. The coefficient of thermal expansion contraction is dependent on the voids in the mineral aggregate, VMA, and percentages of the asphalt mixture component. In other words, the volume of the mixture and total volume of the mix itself. The range of the coefficient of thermal expansion and contraction for the individual mixture components is also displayed on the slide and used to determine the coefficient of expansion and contraction of the entire mix itself. So the B binder, B aggregate is simply the coefficient of expansion and contraction of the binder and of the aggregate. This is combined to estimate or calculate the coefficient of the expansion and contraction of the entire mix itself. Again, the coefficient of thermal expansion and contraction can be calculated by the program, or a user could enter values specifically for different aggregates and mixtures. For the global calibration process, the program was used to calculate the coefficient of thermal contraction and expansion for all flexible pavement sites. The transverse crack depth is calculated using fracture mechanics, using the Paris law. The tensile stress intensity factors were calculated from a finite element response program for many different pavement structures, climates, and asphalt mixture conditions. The results from these computations of the stress intensity factors were used to develop artificial neural networks that are included in the pavement MED software to determine the stress intensity factors for simplicity and ease of computation. The fracture parameters of A and N are defined and explained in a later session of this module. So basically, the pavement ME design program predicts the change in crack depth once the crack initiation starts. So with a crack initiation after it begins, then the change in crack propagation with depth is defined by the change in the stress intensity factors and the asphalt mixture fracture parameters of A and N, which we will define later. The cracking length model to determine the crack spacing is the empirical part of the transverse cracking model. The calibration factor, minimizing the difference between the predicted and measured or observed length of transverse cracks, is applied to the crack length model. In addition, the definition for when a predicted crack becomes a real crack that can be observed and measured at the surface is empirical. The definition of a crack calculated by the model is when the tip of the crack propagates through half the asphalt layer thickness of the entire asphalt layer thickness included in the simulation, not just the asphalt wearing surface. In summary, the length of transverse cracks is a function of the probability that the crack length exceeds the layer effective thickness of H. A normal distribution of the crack depth is applied to determine the length of the crack. So the crack depth, or the length of cracking, is a function of the crack initiation plus the tensile stress and tensile stress intensity stress intensity factors. The length of cracking across the project is simply a function of the probability when that crack length exceeds, or crack depth exceeds, the thickness H of the total asphalt layer. Thermal or transverse cracks develop at the surface and propagate downward through the asphalt wearing surface and other asphalt layers with continued temperature cycles and colder temperature events. This crack initiation and propagation is predicted by two techniques: thermal fatigue and fracture mechanics. Thermal fatigue identifies when the transverse crack occurs or initiates at the surface, while the fracture mechanics approach determines the time it takes for the thermal initiated crack to propagate through the asphalt layers. Earlier versions of the software used the thermal fatigue to determine when the crack initiated at the surface, but used fracture mechanics to determine the time of when the cracks propagated through the asphalt layer. The more recent version of the software uses or relies on the fracture mechanics approach in predicting both crack initiation and crack propagation. Thus, the propagation of crack depth, or delta C, is defined by the change in the stress intensity factors, delta K. The A and N variables are the fracture parameters of the fracture mechanics approach to estimate the change in crack depth and or speed at which the cracks propagate through the asphalt layer with the application of continued cooling cycles. The A variable is related to and determined by the N variable and other mixture parameters of the wearing surface. Specifically, the modulus of the wearing surface measured in accordance with the indirect tensile strength, E asphalt and E asphalt, and the mixture tensile strength measured in accordance with AASHTO T322, the mixture tensile strength measured in accordance with AASHTO T322. The N fracture mechanics variable is defined on the next slide along with determining the stress intensity factor K. The K sub T and beta sub T variables are calibration coefficients, which will be defined shortly within this module. AASHTO T322 measures the indirect tensile strength of the asphalt mixture. The maximum tensile strength is defined at 14 degrees Fahrenheit and assumed to be constant at lower temperatures. This assumption is made for simplicity and ease of computation in the simulation. At very cold temperatures, as noted previously, the indirect tensile strength will decrease, as shown on this slide, because microcracks start to develop at the interface between the aggregate surface and binder. The reduction in tensile strength is not simulated in the Pavement ME software, as we previously mentioned. The stress intensity factor K is defined or determined from the current crack length and the far field stress from the response model at the depth of the crack depth, at crack tip. The N variable, or the N fracture mechanics variable, is defined from the indirect tensile creep compliance curve measured in accordance with AASHTO T322. So the stress intensity factor is defined at the crack tip based on the far field response model at a depth of the crack tip in PSI, and it's a function of the current crack length or crack depth, and N, the fracture mechanics, is a function of M, which is a constant derived from the indirect tensile creep compliance curve. And A of the fracture mechanics parameter was previously defined, but is a function of the stiffness of the asphalt, the strength, indirect tensile strength of the mix, and N, which is a function of the indirect tensile creep compliance curve. The beta T is a calibration parameter, and KT is also a calibration parameter, but related to the laboratory measured creep compliance and strength values. As noted previously, the indirect tensile creep compliance determines how fast or slow the tensile stresses build up with decreases in temperatures. The more compliant the asphalt mixture, the lower the predicted length of transverse cracks. Thus, for the mixtures illustrated in this graph, the lower the predicted length of cracks, for the more compliant the asphalt mixtures. As such, for the mixtures illustrated in this slide, the Warren as defined as the Warren mixture, the Warren creep compliance mixture, is more resistant to transverse cracks because it is more compliant. In other words, for the Warren creep compliance of the Warren mixture, lower transverse cracks will be predicted. In comparison, the Blair mixture, what is defined as the Blair mixture, is the least compliant of all mixtures shown in the slide and will be least resistant to transverse cracks, or a larger amount of transverse cracks will be calculated for the Blair mixture because it has poor creep compliance. Again, the reference temperature for the creep compliance master curve is a negative 20 degrees Fahrenheit. The KT variable is the laboratory asphalt mixture calibration factor, which is mean annual air temperature dependent. The reason for the dependency on mean annual air temperature for the case of T variable is related to other transverse cracking mechanisms that are excluded from the Pavement ME design software, namely shrinkage and thermal fatigue. So, as mean annual air temperature is less than or below 57 degrees Fahrenheit, the occurrence of cold temperature events represents the predominant mechanism for transverse cracking. A mean annual air temperature greater than or above 57 degrees Fahrenheit is where shrinkage and or thermal fatigue play a larger role in the occurrence of transverse cracks. As mentioned previously, the values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results of more recent global calibrations. the coefficients and exponents of the transfer function, including the calibration coefficients, are included in the output report for the Pavement ME design software. So, in summary, the calibration coefficients of K sub T is dependent upon the mean annual air temperature, which was defined through the global calibration process. The transfer function for transverse cracks is displayed on this slide. The length of transverse cracks is defined by a regression coefficient from the global calibration effort. This is defined as the B subscript T1 and is defined or was defined through global calibration. The standard normal distribution of the crack depth relative to the total layer thickness defines the transverse cracks, or the distribution of transverse cracks, which is also related to the total thickness of all asphalt layers, the crack depth. C sub D is the crack depth predicted through the stress intensity factors, delta K, and properties of the wearing surface, the creep compliance of the wearing surface, as well as the indirect tensile strength of the wearing surface, and the standard deviation of the log of the depth of transverse cracks along the pavement. This is also a calibration parameter that was used during the global calibration process. So it is a standard factor, the standard deviation of the log of the depth of cracks along the pavement. And it's defined through calibration and not through the stress intensity factors or other properties of the asphalt. So it defines the distribution and not the actual crack depth. Once the crack depth is defined, the distribution is used to evaluate the changing crack depth over time. Reliability was discussed in detail in Module 3 and how it is applied in the Pavement ME design software. The standard deviation of the residuals for the transverse cracking of flexible pavements is displayed on the slide. The standard deviation of residuals is used to determine the reliability as related to transverse cracking of flexible pavements and is mean annual air temperature dependent, as well as input level dependent. So for input level 1, where creep compliance, indirect tensile strength are measured, the standard deviation of the residuals for transverse cracking for those sites with mean annual air temperature less than 57 degrees versus mean annual air temperature greater than 57 degrees Fahrenheit. And so you can see that for each input level, the error or standard deviation of the residuals do increase for the sites in the warm to hot climates versus sites that are in a cold climate where cold temperatures predominate in determining the total length of transverse cracks that are predicted. Now remember, input level 1 uses laboratory measured indirect tensile creep compliance and strength values, while input level 3 uses the calculated or predicted indirect tensile creep compliance and strength values using the regression equations embedded in the Pavement ME design software. There definitely is a bias between input levels 1 and 3. Also, the standard deviation of the residuals also increase from input level 1 to input level 3. So the standard deviation of the residuals for input level 1, where the creep compliance indirect tensile strength are measured, are less than input level 3, where the creep compliance and indirect tensile strength are predicted or calculated within the program, Pavement ME design program itself. Input level 2 in earlier versions prior to version 3 used the measured indirect tensile creep compliance value, but only measured at one temperature, predominantly 14 degrees Fahrenheit. The new input level 2 calculates the creep compliance values from the input level 1 measured dynamic modulus values, which removed the bias between input levels 1 and 2, but not the bias between input levels 1 and 3. The use or revision for input level 2 was discussed in Module 4-4-5 on the inputs to the Pavement ME design software, at least for the asphalt mixture-related inputs. An important observation regarding the error term or residual errors between the measured and predicted lengths of transverse cracks is the magnitude or the error or the standard deviations of the residuals between the measured and predicted transverse crack is the difference identified below and above a mean annual air temperature of 57 degrees Fahrenheit, kind of as shown on the previous slide. So below a mean annual air temperature of 57 degrees Fahrenheit, cold temperature events predominantly dictate the length of transverse cracks, or basically controls the occurrence of transverse cracks. While above 57 degrees Fahrenheit, which is represented by warm to hot climates, is where other mechanisms of shrinkage and or thermal fatigue have a greater influence on the occurrence of transverse cracks, which are not simulated in the Pavement ME design software. Thus, the error is greater in the warmer to hot climates because of other mechanisms being grouped under a single calibration coefficient or constant, which is the beta sub T value. This section is a summary of the materials presented and covered under Module 6.1.2 for transverse cracking of flexible pavements. There were 5 learning outcomes from Module 6.1.2, which were presented in this module and included: we defined and explained the transverse cracking of flexible pavements and how they were measured. We defined the mechanism of transverse cracks of flexible pavements. Remember, the asphalt wearing surface properties define the crack initiation and propagation of transverse cracks through the different asphalt layers. Only the properties of the wearing surface are used. We define the fracture mechanics approach and concept used to predict transverse cracking. We describe the transfer function used for predicting transverse cracks in flexible pavements. And finally, we listed the asphalt wearing surface properties and test procedures used in support of the transverse cracking transfer function. So this ends Module 612 on transverse cracking. The next sub-module of the training course sequencing is Module 613 on fatigue cracking of flexible pavements.